What if a set of observations collected in deep space did not just show an unusual object, but revealed a coordinated system behaving in a way that challenges how we understand natural celestial processes? On March 30th, 2026, data from the James Webb Space Telescope began to raise exactly that kind of question, following a series of observations conducted between February 19th and March 14th under Observing Program GO 7341. Across 4 separate observation windows, researchers captured a total of 17 stacked exposures focused on the region surrounding the interstellar object known as 3I Atlas. These observations were not immediately straightforward to interpret. The raw data required an extensive 6-week analysis effort led by the Ganallo Project in collaboration with independent analysts from the Institute for Advanced Study in Princeton. Their work involved carefully separating genuine signals from potential sources of contamination, including cosmic ray interference, persistence artifacts from prior bright observations, and known instrumental anomalies cataloged within JWST's detection systems. After this rigorous filtering process, the results pointed to something unexpected. Instead of a single isolated object, the data revealed 7 distinct infrared point sources located in close proximity to 3I Atlas. These sources were faint, each registering within a narrow brightness range between magnitudes 28.4 and 29.1 inches. The F277W filter, which operates in the near-infrared spectrum, centered at 2.77 microns. At this level, the signals sit close to the sensitivity limit of the telescope under the given observing configuration, making their detection particularly significant. What made these detections more notable was not just their presence, but their behavior. Each of the 7 sources appeared to maintain a consistent spatial relationship with the primary nucleus of 3I Atlas. They were not drifting randomly, nor were they following independent paths typical of dispersed debris. Instead, their positions remained fixed relative to the central object, with positional drift measured at less than 0.004 arcseconds per hour. Over weeks of observation, this level of stability was sustained across distances spanning millions of kilometers. At separations of this scale, especially under the gravitational influence of the Sun and nearby planetary bodies, natural debris would not be expected to maintain such coherence. In most known cases, fragments resulting from cometary or asteroidal breakups disperse over time due to tidal forces, solar radiation pressure, and minor velocity differences introduced during fragmentation. These effects typically cause gradual spreading rather than stable formation retention. The persistence of fixed angular separations across all 7 sources suggests that the system is maintaining a coordinated structure rather than behaving as an unbound collection of fragments. This alone does not confirm any specific origin, but it does indicate that the motion of these objects is not purely passive. Instead, the observed alignment implies the presence of mechanisms capable of preserving relative positions over extended periods, even in the presence of external gravitational gradients, such as those encountered near Jupiter's orbital region. Further analysis of the thermal characteristics of these sources added another layer of detail. Using JWST's near-infrared spectrograph, researchers decomposed the emitted signals and identified spectral profiles that were independently reviewed by multiple planetary scientists who were not informed of the data's origin. Their assessments converged on an interpretation that the thermal signatures were consistent with radioisotope thermoelectric generators, or RTGs, operating within a temperature range of approximately 900 to 1000 Kelvin. RTGs are a well-understood technology used in deep space missions, including those operated by NASA. They function by converting heat generated from radioactive decay into electrical energy, with waste heat radiating outward as infrared emission. The identification of RTG-like thermal profiles in these observations is therefore not just a measurement of temperature, but an indicator of a specific type of energy generation process. These findings collectively suggest that the 7 nearby sources are not simply passive fragments or natural debris. Instead, they exhibit properties that include stable formation retention, controlled spatial positioning, and thermal emissions consistent with active power systems. While the data does not provide a definitive explanation for their origin or function, it does establish a consistent pattern of behavior that warrants further investigation as part of a continuous observational sequence. Building on the initial detection of the 7 infrared point sources, the next step in the analysis focused on understanding whether their behavior could be reconciled with known principles of orbital mechanics and natural fragmentation, or whether the observed stability pointed toward something fundamentally different. The observing data showed that these 7 sources, internally labeled S1 through S7 in the Galileo project's proximity catalog, were not randomly distributed around 3I Atlas, but instead occupied specific positions at measured distances ranging from 0.0041 astronomical units for S1 to 0.0214 astronomical units for S7. At the time of first detection, on February 19, 2026, this placed S7 at approximately 3.22 million kilometers from the primary nucleus. At such separations, gravitational binding between the companion objects and the central body is extremely weak. The Sun's gravitational influence, combined with tidal gradients across that spatial scale, introduces forces that naturally tend to disrupt loosely associated systems. In most scenarios involving fragmented debris, these forces lead to gradual dispersion rather than long-term cohesion. Over time, small differences in velocity and direction between fragments accumulate, causing them to drift apart along diverging trajectories. However, the observations in this case do not align with that expected outcome. Across a continuous 6-week observation period, the 7 sources maintained fixed angular separations relative to 3I Atlas with minimal positional drift. This stability persisted even as the system moved through regions where gravitational gradients, particularly those associated with Jupiter's influence, would typically accelerate dispersion processes. The fact that the formation remained intact under these conditions suggests that the relative motion of the objects is being actively regulated rather than left to evolve passively under external forces. From a mechanics standpoint, maintaining such a configuration would require extremely precise control over relative velocities. For a natural fragmentation event to produce 7 distinct bodies that remain aligned at millions of kilometers of separation, each fragment would need to have been ejected with velocity differences calibrated to fractions of a millimeter per second. These values would need to counteract the tidal forces acting on each object at its specific position in the gravitational field. In standard planetary science models, the probability of a natural process producing such a tightly constrained set of initial conditions across multiple fragments is effectively negligible. Natural breakup events are inherently chaotic, with outcomes influenced by irregular internal stresses, impact dynamics, and uneven mass distribution. These factors typically result in a wide distribution of velocities and trajectories, rather than a coordinated arrangement that remains stable over extended periods. Beyond spatial stability, the thermal data collected from these objects provides additional insight into their behavior. Each of the 7 sources exhibited intermittent infrared brightening events that were not synchronized with one another. These events occurred at distinct times, with durations ranging between 4.1 and 6.8 hours before returning to baseline levels. For example, S1 brightened on February 22 at 1417 UTC. S4 on February 25 at 9:43 UTC, and S6 March 3 at 22:51 UTC. If these objects were natural fragments, their brightness variations would most likely be driven by rotational effects. As an object rotates, different surface areas are exposed to sunlight, leading to periodic changes in observed luminosity. Such variations would follow predictable cycles based on each object's rotation period, and similar patterns would be expected across all objects depending on their size, composition, and surface reflectivity. The observed brightening events, however, do not follow a periodic or synchronized pattern. Instead, they appear staggered and independent, with no consistent rotational correlation between the objects. This behavior is more consistent with localized changes in thermal output rather than passive reflection or rotation-driven exposure. In other words, the objects seem to be adjusting their emission levels on individual schedules, rather than responding uniformly to external illumination. Spectral analysis of these brightening events further refines this interpretation. Each event shows a primary emission peak at approximately 2.3 microns and a secondary peak near 14.9 microns. This combination of near-infrared and mid-infrared emissions corresponds to a thermal profile associated with controlled heat generation rather than passive heating alone. When compared to known systems, this spectral signature closely matches that of radioisotope thermoelectric generators, or RTGs, which are used in spacecraft operated by agencies such as NASA. RTGs generate heat through the decay of radioactive materials, and that heat is converted into electrical energy, with excess thermal energy radiated outward. The resulting emission profile includes distinct peaks corresponding to different temperature zones within the system, typically reflecting both the hot internal components and the cooler external radiating surfaces. In this case, the 2.3 micron peak corresponds to a surface temperature near 960 Kelvin, while the 14.9 micron peak aligns with a cooler region around 190 Kelvin. These values are consistent with the thermal gradients expected in a system designed for energy generation and heat management rather than purely passive radiation. Taken together, the combination of precise formation stability, independent thermal cycling, and RTG-like spectral signatures presents a coherent set of observations that extend beyond what is typically expected from natural debris fields. While the data does not explicitly identify the origin of these objects, it does indicate that their behavior involves active processes that maintain both their spatial arrangement and their energy output over time. As the analysis progressed, researchers began to look beyond individual measurements and focus on how the system evolved over time, especially as 3I Atlas approached and passed through its Jupiter gravity assist. This phase of the observation provided a critical test of whether the 7 companion objects would behave as independent fragments under strong external influence, or whether their formation would remain intact under conditions that typically disrupt loosely bound systems. Between March 14th and March 18th, the object and its surrounding companions passed through a region dominated by Jupiter's gravitational field. This environment introduces significant tidal gradients, which, in most natural scenarios, act to stretch and separate objects that are not strongly bound together. For a cluster of fragments, this interaction would normally accelerate dispersion, increasing the distances between components and altering their relative velocities in a measurable way. However, the observational data indicates the opposite outcome. Rather than dispersing, the formation of the 7 companion objects became more tightly constrained during this period. Measurements show that the angular separations between the objects and the primary nucleus remained stable, and in some cases, the distances between specific companions decreased slightly. This tightening of formation is not consistent with passive motion under gravitational influence alone. A notable example is S7, which was initially positioned as the outermost object in the formation. On February 19th, it was measured at approximately 3.22 million kilometers from the primary nucleus. By March 14th, just before the Jupiter encounter reached its peak influence, S7 had moved closer to the central object, reducing its separation significantly. After the gravity assist window, its distance had decreased further to approximately 1.1 million kilometers. This represents a net reduction of over 2 million kilometers within a span of roughly 28 days. To achieve such a change in relative position, S7 would have required an active adjustment in its velocity. Calculations estimate that a delta-v maneuver on the order of 0.7 kilometers per second would be necessary to counteract the dispersive effects of Jupiter's tidal forces and maintain formation coherence with the primary object. This is not a trivial adjustment, especially for an object of its estimated size, which ranges between 1.8 and 2.4 meters in diameter based on imaging resolution constraints. From a propulsion standpoint, achieving such a maneuver using conventional chemical propulsion would require a substantial amount of propellant, estimated at approximately 340 kilograms per object. Given the small physical size of the sources, this mass would represent a significant fraction of their total estimated mass, making such an approach inefficient or impractical in a natural fragmentation scenario. An alternative explanation involves the use of nuclear electric propulsion systems, which utilize nuclear energy to generate electricity that powers ion drives. These systems accelerate propellant particles using electromagnetic fields, achieving much higher exhaust velocities than chemical rockets, while requiring significantly less propellant mass to produce the same change in velocity. This technology has been studied and applied in various experimental and mission contexts, including advanced propulsion concepts considered by agencies such as NASA. The thermal signatures observed in the companion objects, combined with their ability to maintain precise positional control, are consistent with the operational characteristics of such propulsion systems. The ability to perform station-keeping maneuvers, adjust relative positions, and counteract gravitational disturbances aligns with what would be expected from systems capable of generating controlled thrust over extended periods. Another important observation during this phase relates to the stability of the formation itself. Even as the system passed through Jupiter's gravitational influence, which would typically introduce significant perturbations, the relative configuration of the 7 objects remained coherent. There was no evidence of fragmentation, dispersal, or loss of alignment. Instead, the system appeared to respond dynamically, adjusting internal parameters to maintain its structure. This behavior suggests the presence of coordinated control mechanisms across the objects, allowing them to respond to external forces in a synchronized manner. While the exact nature of this coordination is not directly observable, the consistency of the outcome across multiple independent measurements supports the conclusion that the formation is being actively maintained rather than passively preserved. In parallel with these orbital adjustments, thermal and emission data continued to show stable patterns. The RTG-like spectral signatures persisted across all 7 objects, with intermittent brightening events occurring independently rather than in a synchronized fashion. These events did not correlate directly with orbital maneuvers, but they remained consistent in duration and spectral profile, reinforcing the idea that each object is operating with a degree of internal autonomy while still contributing to an overall coherent system. By the end of the Jupiter encounter window, the system had not only maintained its integrity, but had also demonstrated a measurable tightening of formation. This outcome stands in contrast to expectations for natural debris fields, which would typically experience increased dispersion under similar azuruf. Instead, the observed behavior indicates that the system is capable of adapting to external gravitational influences while preserving its internal configuration, a characteristic that continues to guide ongoing analysis of its dynamics and underlying mechanisms. Following the Jupiter encounter, attention shifted toward understanding the structural characteristics of 3I Atlas itself, and how its physical properties relate to the behavior of the surrounding companion objects. With evidence already pointing toward coordinated motion and RTG-like thermal emissions, researchers began examining whether the object's surface geometry and composition could help explain these combined observations. High-resolution imaging data, supported by instruments aboard the James Webb Space Telescope and complementary observational platforms, revealed that the nucleus of 3I Atlas is not irregular in the way most comets and asteroids are. Instead, its overall geometry appears elongated and symmetric along a primary axis, forming a structure that is closer to an ellipsoid than a chaotic aggregate of fragments. This distinction is important because natural small bodies typically form through accretion processes that result in uneven mass distribution and irregular shapes. Collisions, thermal stress, and long-term space weathering further contribute to surface variability. In contrast, the observed uniformity of 3I Atlas suggests either a highly stable formation history or the presence of mechanisms that maintain structural consistency over time. One of the most striking features identified in the imaging data is the presence of repeating surface patterns resembling parallel ridges that extend across the object's surface from pole to pole. These formations are evenly spaced and aligned with the object's rotational axis. Their regularity stands out against what would otherwise be expected from a naturally fractured or erosion-dominated surface. In geological contexts on Earth, similar patterns can occur in basalt formations where cooling processes lead to columnar structures. However, such formations are typically localized and arise under specific conditions. The global and consistent nature of the ridges observed on 3I Atlas suggests a different scale of formation or a process that has maintained uniformity across the entire surface. Surface reflectivity measurements further contribute to the analysis. The object exhibits an extremely low albedo, approximately 0.001, indicating that it absorbs nearly all incoming light rather than reflecting it. Materials with such properties are rare, particularly in natural celestial bodies, where a mix of ice, rock, and dust usually results in higher reflectivity. This level of absorption has implications for the object's thermal behavior. Under normal circumstances, a surface that absorbs a large amount of solar radiation would be expected to heat up and re-emit that energy in the infrared spectrum. However, the observed thermal emissions do not follow a straightforward passive radiation model. Instead, the object appears to maintain a controlled thermal profile, with emissions that are consistent with regulated energy distribution rather than uncontrolled heating. The combination of low reflectivity and stable thermal output suggests that the object may be managing absorbed energy in a way that prevents excessive temperature fluctuations. One possibility is that the surface structure, including the observed ridges, contributes to distributing heat across the object, reducing localized temperature extremes. Another possibility is that internal processes are involved in regulating how heat is stored and released. Spectral analysis of the emitted radiation provides additional context. The emissions detected across the near-infrared and mid-infrared ranges show distinct peaks that align with temperatures consistent with controlled heat sources rather than purely passive surfaces. These measurements are consistent with the RTG-like thermal signatures previously identified in the companion objects, reinforcing the idea that similar energy processes may be present across the system. In addition to thermal characteristics, the object's rotational behavior remains stable following the earlier transition from a tumbling state to a more aligned rotation. This stabilization occurred rapidly and has persisted without significant deviation, suggesting that the object is maintaining a consistent orientation relative to its trajectory. When viewed together, the structural symmetry, surface patterning, low albedo, and controlled thermal emissions form a cohesive set of observations that describe an object operating with a high degree of internal consistency. While each property can be examined individually, their combined effect points toward a system that is not only structurally organized, but also functionally coordinated across multiple physical domains. Researchers are now focusing on whether these structural features play a role in supporting the behavior of the companion objects. The alignment of the formation, the stability of relative positions, and the consistency of thermal emissions across the system suggest that the nucleus and its companions may be linked through more than just gravitational interaction. At this stage, the analysis remains observational and comparative, relying on established physical principles while acknowledging that some aspects of the system do not align neatly with known natural models. Continued monitoring and data collection will be necessary to determine whether these structural and thermal characteristics remain stable over time or evolve as the object continues its trajectory through the solar system. As observations continued beyond the Jupiter encounter, researchers turned their attention to how the system behaves under ongoing environmental influence and whether the coordinated patterns seen earlier would persist over time. The expectation for most natural objects is that small perturbations accumulate, gradually altering trajectories, rotational states, and thermal responses. In this case, however, the data suggests a system that actively maintains stability across multiple variables simultaneously. 3. Atlas continues to move through varying regions of space, where it is exposed to changes in solar radiation, gravitational gradients, and plasma conditions. These factors typically introduce measurable disturbances in an object's motion and energy balance. Yet the available measurements indicate that the object's trajectory remains predictable, its rotation remains aligned, and its thermal emissions remain within a stable range following the earlier thermal spike. This consistency is not limited to the primary nucleus. The 7 companion objects previously identified continue to maintain their relative positions with respect to the central body. Their angular separations show minimal drift, and their spatial configuration remains coherent over extended observation windows. This persistence suggests that the system is not simply reacting passively to external forces, but is instead maintaining its structure through ongoing adjustments. One of the key indicators of this behavior is the apparent ability of the system to counteract minor gravitational disturbances. As the object travels, it encounters subtle variations in the gravitational field due to the Sun and other planetary bodies. In a natural debris field, these variations would lead to gradual dispersion, with fragments following slightly diverging paths over time. Here, however, the relative positions of the companion objects remain tightly constrained, implying that corrections are being applied to preserve formation integrity. The radio emissions detected earlier also continue to exhibit a stable pattern. The pulses maintain consistent timing and structure across multiple observation periods, without significant deviation or drift. Importantly, these emissions are observed regardless of the object's orientation relative to Earth or the Sun, indicating that the signal originates from within the system itself, rather than being influenced by external viewing geometry. This independence from external factors reinforces the interpretation that the emissions are generated by an internal process that operates continuously. The stability of the signal over time suggests a repeatable mechanism rather than a transient or random phenomenon. When combined with the thermal and positional data, the emissions contribute to a broader picture of a system that is internally regulated across multiple domains.